This question is similar to question 9, with the exception that there is force of friction involved. So each block um, has a force of friction acting on it, and it's opposing the direction of motion. And we know that the coefficient of friction between the surface of the blocks and the ground is mu. So there are times in the question when we solve this question where we're going to treat, where we're going to look at the force of friction acting on a single block, or we're going to look at the force of friction acting on all of the blocks as a whole. So if we're going to group all of the masses together, what is the force of friction acting on the entire mass? So let's just do a free body diagram of all masses together. So there's a force F that's pulling it. And then there are 3 forces working against that pull force. And that's F1, or let's make these a little bit more descriptive. We'll say that this is FF1, FF2, and FF3. So that's force of friction. So that would be FF1, FF2, and FF3. So we can collect all of these. So the force of friction acting on the whole mass is equal to force of friction 1 plus force of friction 2 plus force of friction 3. And if we expand these, we know that FF, the force of friction, is also equal to mu m1g, because that's acting on mass 1, plus mu m2g plus mu m3g. Now we can factor out some the terms that are, or the variables that are the same in each term, and that's mu and g. So mu g times m1 plus m2 plus m3. So we see that the force of friction is actually equal to mu times the acceleration due to gravity times the total mass. Now, if each block had a different surface and therefore a different mu value, then we would replace that different mu value at each term. But in this case, the mu is the same, so we don't have to really consider each block separately. We can treat them as one whole. Okay, so let's look at what the acceleration of all 3 blocks are. So we're going to find the acceleration of the system. And to do that, we'll, just like in question 9, what we'll do is we'll treat the entire system as one big block. So we're actually looking at the Fnet of this. So what we have here is Fnet is equal to the force applied, which is pulling all 3 blocks. And then we'll include direction, so we have minus FF. So that's the total of all 3 of these. So if I expand Fnet using Newton's second law, we get ma, where m is, here, let's just fix that, mta, that's the total mass, that's m1 plus m2 plus m3. And then F is known, minus mu g mt. So A, if we solve for A, is equal to F minus mu g mt over mt. Now if we want to find the tension force, so let's say we want to find T1, which is here. Then what we do is, we do, just like in question 9, we look only at the free body diagram of M1. So M1 has a force of tension going to the right, and then it has a frictional force going to the left. But this is not the frictional force FF. It's only the frictional force due to M1, because when we do our FNet statement, we only care about the mass understudy. So if we're looking for T1, then what we do is we go FNet is equal to tension 1 minus FF1, and we rearrange for T1. So that's FNet plus FF1 is equal to T1. And FNet in this case is MA, M1A, plus mu M1G. And then what we can do is we can replace A with this here. So let's do that. I'm just going to erase this. And we get M1 times F minus mu G MT over MT plus mu M1G. That's equal to T1. So does this make any sense? Well, what this is saying is that the tension force has to be equal to the acceleration force plus the force of friction holding it back. And that does make a lot of sense, because the tension force has to overcome friction before it can start adding acceleration to the block M1. So to solve for tension 2, you would do something similar, except the free body diagram would be a little bit more complicated. So let's just erase this here. And then we'll bring back this. And I also want to kind of keep this as well. So we'll work in here. So for T2, our FNet statement looks like this. It's FNet is equal to, we have T2 going to the right, we have T1 going to the left, and we have the force of friction 2 going to the left. So T2 has to be large enough not only to overcome the frictional force, but also to overcome the inertia of a block M1, which wants to kind of stay behind. So we have our FNet is equal to M2A, because that's the block we're interested in right now. That's what our FNet statement is about. And that's equal to T2, which we're trying to find. And actually what we'll do is we'll solve for T2. So I'll move back here a bit. So we're going to add T1 here to the left side, and then we're going to also add FF2, and that's equal to T2. So A is equal to this, because the acceleration of the blocks must all be the same, just like in question 9. And so we get M2 times F minus mu G MT over MT plus T1 is this, so M1 F minus mu G MT over MT plus mu, and just erase this part, plus mu M1G plus, so let's go back here. So this term right here is M2A. This term right here is T1. And then FF2 is equal to mu times m2g, and that's equal to T2. So that's a big one. So this is our answer right here for T2. And this is our answer for T1. And this is our answer for A.